Hello, Tamal.
বল হ্যালো।
Hello.
হ্যালো, শোনা যাচ্ছে?
So, good evening, everyone. Today's lecture will be given by Tamal Guha. He has done his PhD from ISI Kolkata. Now he is postdoc at Julio Chirivela's group at University of Hong Kong. So today he will talk about quantum communication. And Tamal, now what to you? You can start.
Thank you. আচ্ছা, so actually when I was discussed with Shomda about the talk, and when Shomda was asked me for the talk, I thought that I will finish the talk in a one day, at least in 1 hour. But now, after making the complete presentation, it seems that maybe one day is not sufficient to continue. But still, I'll start and see that how it goes. So, the starting point of any quantum communication, though the name is quantum communication, we actually mean communication of quantum system to transfer classical information. So that's why, since the physical system is quantum system, what we are actually trying to communicate or trying to send, that's why we say it quantum communication. But whatever we are saying in this talk, that is only about classical information processing or classical information communication. So the journey starts in Holevo, 1973. Then after a few times, there is a new pathway in the quantum communication in sense of classical information processing. This is this broken maroon path, and there are some important results in this direction. Some by Galavo and Hardy. There is the result by Ambainis. There is some result by Perry, Zane, and Open, and also many other results. And after the 73 results, there is another result becomes important in this direction is 2015 by Frenkel and Weiner. Thereafter, some results by our group, means during my PhD group, and some result by Heinossari and Kirpo. And there is a recent result by Heinossari, Kirpo, and Plavala, Martin Plavala is there. And thereafter, another most recent work by our team means Saptorshi, me, Shutopa, and Julio in 2024. And obviously, there are many open directions still from here. So this blue path is actually our way to travel from this point to this point. And there is, as I said, this broken maroon path, which is kind of a different kind of a path from the perspective of standard classical information processing. Because if you, just for some introduction or for some completeness, that this Galava's paper, these actually means consider a situation where there is a continuous encoding of the information throughout the trajectory of communication. Like this Ambani's result, this is actually requires an additional input to the Bob side before generating the output. So generally called the random access coding kind of thing. Or there is some result by Perry, Rahul Jain, and Jonathan Oppenheim in 2015, which is also in the same journal of this Ambani's, but obviously in this different form. So we are not going to this maroon path, and our goal is to follow this blue trajectory. Well, what is the scenario of a classical information processing or classical communication via any system? That may be a classical system, maybe a quantum system, whatever maybe. So the thing is that the same that Alice, she has some number of random variables or random messages. She want to convey this message to Bob. And what Bob has, Bob a priori or initially has some distribution over the possibility of each of the random variable. So it may be x1, maybe x2, maybe x3, and like this, there will be some probability of px1, probability of px2, or probability of px3. Now what happens? Alice means the sender, encodes her message in a physical system then send it through the channel, and Bob get that system, obviously in some changed form if the channel is not an identity channel, and then Bob do some measurement or do some observation allowed in that theory, get some another random variable y, which may be exactly correlated with x, which may be anti-correlated to x, which may be random with x, and anything depends upon n and the procedure of decoding, procedure of encoding. So finally, at the end of the day, what happens if Alice wants to send a message x1, Bob receives, suppose, another random variable y1, the probability of getting this y1, this probability is get enhanced and other probability get decreased. Because you see, in the initially, if you remember the initial picture here, all the probabilities, at least for our consideration as an example, all the probabilities are completely unbiased. After getting the random variable, one of the probability get increased and other gets decreased. And you can understand that if it is a perfect channel and perfect encoding, perfect decoding kind of thing, what will happen if Alice wants to send x1, one of the probability will become a is exactly one value and other will get decreased to 0. But in general, it will be a redistribution of the probabilities. And how to quantify this one? Well, one standard measure to identify the difference between these two distribution is basically the mutual information. Now, this we know that the scenario of classical communication, there could be a maximization over the probabilities, which the initial probability about the random variables, maximization over the encoding possibilities, the maximization over the decoding possibilities, and they have to maximize the mutual information between the input random variable x and the output random variable y. And there is another way that you can define the asymptotic capacity. Suppose you have small n number of times this channel, you can do the channel n times use and divide it, regularize by some n, and do the actual capacity. So this is actually the standard definition of capacity. You can also see this reference by Holevo in 1973. But whatever it is, it finally says that as a consequence of this result, one can show that the qubit, a single quantum two-dimensional system or d-dimensional system, cannot communicate more than a classical bit. If it is a noiseless qubit communication, it cannot communicate more than a C bit, a perfect classical bit communication, or maybe a DIT one. So this one is an established result. So no problem with it. But one thing is important. You see, if you expand the expression of mutual information, you will see a strange behavior. What is that strange behavior? That mutual information not only captures that, so this one is the picture in the right side, this pink one, the orange one. This one is actually showing the after getting the information from Alice, the probability distribution. And this one is the probability distribution beforehand. So if you expand the expression of mutual information, you will see that it doesn't only capture that how much the particular random variable probability is get increased, but it also captured how much amount the other random variables like y2, the probability of x2 to y2 is get decreased, the probability between x3 and y3 get decreased. These also captured by mutual information. Well, it has no problem apparently, but there could be a scenario where how much the other random variables, say y2 and the probability of y2 and y3 has decreased, that is not at all important. The most
Tamal,
important. Hello?
Comm has a question. So please ask.
Yeah. Oh, hello, Tamal. Can you hear me?
Yeah.
Yeah. Okay. So I'm probably a bit confused when you say that this probability of y is the probability of distribution of y after getting the information. So there should be a condition on x, right? on this probability
Yeah. Actually, I have implicitly that in mind because this picture is conditioned that Alice has sent. Yes, obviously.
X, right?
Yes.
Okay, so this distribution is different for different X's.
Yeah, obviously. That actually I have in mind because you see in this picture I have said that Alice is sending X1. That's why this is the probability distribution. Obviously, it is there.
Okay. Thanks.
Arugda, you can.
Can you hear me?
Yeah.
Achha, when you have written that a qubit cannot be communicate more than a C bit, are you trying to say that using a C bit, whatever you can establish IXY, that is qubit, whatever IXY can establish by the qubit, it is not more than that established by the C bit?
Yes. Perfect.
That's the thing, huh?
Yes. Obviously.
Okay.
Even in the multiple round.
Multiple copy.
Yes.
Yeah. Okay.
Okay. But it could be possible that there can be a scenario where only the increment in probability is really necessary. We are not at all bothered how much the other probability get decreased. It is possible, right? How it is possible? Let's consider a task. The task is like that. Bob has 3 boxes, and one of the boxes contains $1. Alice knows that which box is containing the $. Alice wants to convey Bob that, well, this first box wants to convey the $. You see, in this scenario, beforehand, Bob has completely random distribution about x1, x2, x3. Now, if the actual input is x equal to 1, then Bob has to better know that the first box contains the $. It is not at all important that how much he has less information that the $. Is not contained in the second box or the $. Is not contained in the third box. The only thing is that how much information he got that the $. Is actually in the first box. But if you consider the mutual information, then it is tricky because mutual information say, oh no, you should not check that how much Bob know that the $. Is contained in the first box. But it is also important that how much Bob can say that no, the $. Is not the second box, that the $. Is not in the third box. That is also important in the terms of mutual information. But these guys, Frenkel and Weiner, they pointed out this thing, that this is an important fact, that there could be a possible communication scenario where it is only important that how much you can enhance that particular random variable value. You forget about other things. So for this kind of a game, you can define something called $ capacity, which is 1/3, means any of the boxes has equal probability. And the thing is that whenever x equal to xk, y should be equal to yk. And you sum over of this. This could be a capacity. In principle, the capacity can be a huge thing. If you think like this, that we can go beyond mutual information. In a most general sense, Alice has m number of random variables. Bob has n number of random variables. They are designing a channel matrix that given x1, what is the probability that Bob gets y1, blah, 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 blah. What is the probability that given xm, Bob gets yn? So this is called a channel matrix. This should be the general structure of classical capacity one should convey. The question, the form is raised initially by Frenkel and Weiner and then generalized for any arbitrary GPTs, even multiple copies by Gallardo in 2017. But what it is saying that you may consider whatever may be the general thing, there could be a m input and n output, but still a qubit cannot communicate more than a C bit. Even more precisely, a qudit cannot communicate more than a CDit. So QDMN is exactly equal to CDMN. Well, if this is true, then what is the meaning of this today's talk? Because this is the end, right? You can consider any arbitrary general channel matrix, M input, N output, you will get the exactly same thing. So what is the meaning of talk, giving a talk on this topic? No. Because if you look at it very precisely, you will see that they are actually saying that not exactly these two things are same, but with the assumption that there is an unbounded amount of shared randomness. What is that shared randomness? That could be a, I will come to that shared randomness part later. But to be precise, there is an additional thing which is called shared randomness. Now, this sparks the question mainly in our community, in my previous research group also, and recently Teiko Heinossari and his collaborators.
I think Nirvana has a question. Nirvana, you can unmute yourself and ask the question.
Tamal, I have one question regarding this this equation. In the previous, if you go to the previous equation, like yes. So the thing is that when you are saying that the left hand side is equal to the right hand side, what are these? These are matrices, or you are talking about some
Sorry. Yes. It is the state of all possible matrices. Hello. Can you? This is the set of all possible matrices with M input and N output.
Okay, so you are saying that both the sets are same.
Exactly.
So that means you are trying to bring in a concept of a communication matrix, and you are showing that the two communication matrices are same.
Yes. Actually, Nirvana, actually this talk is kind of a hodgepodge because I have made some different official talk, and now I have made some talk for this weekly seminar.
Okay. No
so
problem.
This thing I will explain later maybe. But yes, obviously this is all possible matrices. Yes, exactly.
Okay. Fine.
Okay. So
one more thing. Sorry. One more thing. When you say that, like, this is qubit can, like, this result, like, it's for that when your payoff is of that form, right? Where you have the sum over p of yk, xk, sum over k.
This one. No. Yeah. For that game, obviously this is the payoff. But in general, the payoff can be anything, right? On the matrix. Even you can say just generate this matrix. That could be a task.
So this is any kind of payoff as long as it is summed over all the.
Not necessarily sum over. It may be just a particular term. Just a single.
It can be something like a worst case scenario. Also.
Yeah, exactly. So in general, that's why we are saying that in general, whether this total channel matrix, this input output matrix can be simulated. That is the question in general.
Okay. Thanks.
Tamal, can I make a comment?
Yes.
Yeah, Shom, you can think that matrix has how many elements? Many elements, no? Whatever function from this element to real number you can consider, any function you can take.
Right.
Linear, non-linear, whatever.
Exactly.
Extremely non-linear, logarithm, tan, hyperbole, whatever you can think. It is so generic. Because it is
it is just a map.
No, it is. You look into this statement of Tamal's statement. He's talking about the set is identical. If set is identical, what function you will thought about? No problem, no?
The matrix is basically same.
The matrix itself is identical. Okay. Thanks.
Well. Okay. Now there is some problem. We are saying that PQD M to N means this is the collection of all M input N output matrix and the collection of all M input N output matrix in classical D-dimension plus SR. But you see, this is an in principle result. Why in principle result? Because there is no bound on this SR. Because it may be two coins, head and tail. Okay, so SR means I have one coin and another party has another coin. Whenever I will have head, he will have head. And whenever I will have tail, he will also have tail. Also has tail. But or it may be some kind of correlation, but not exactly random, that I can randomly have head tail and he can randomly have head tail. Not like that. Any kind of correlation we had between 2 points.
Tamal,
Or,
can we say shared randomness as like some previously agreed upon strategy?
yes, 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 you can say. But still there are some concepts, means to me, yeah, you can obviously say that it is actually a agreed upon strategy. But if you think very critically, then agreed upon strategy, you can say that, well, I and you can agreed upon with some strategy that, well, in the first round, we will do this. In the second round, we will do this. Like,
Yes.
but yeah, effectively shared randomness and with this, among these, there is no difference. But if you think critically, shared randomness is something like that. You don't know that in the particular round what you have to do. The coin, the result of the coin will determine that whether you have to do this or you have to do this, because it will give you head or tail. And something like pre-shared strategy is also exactly like SR mathematically, but it is somehow defined that, well, in the 10th round, I will do this one and you will do this, this one. Now, if you call about truly shared randomness, in the 10th round, we will throw a dice and get a result. Depending upon that result, we will fix that. This is kind of a difference, but effectively, I am again saying mathematically, technically, these two things are exactly same. So you can think that it is kind of a pre-shared strategy. Yes.
Okay.
But it may happen that the sender and receiver are two completely unknown person. They never have met earlier.
Yes.
Then you can say that, well, pre-shared strategy or this kind of a different kind of a thing. So people encounter this thing like it is an in principle result, and you can actually have unbounded shared randomness, because there could be two dice, there could be any integer correlated, there could be any uncountable numbers in both sides, and that can be correlated. So this is one particular criticism, which is kind of a philosophical criticism. But if you say, can there be some operational criticism? Yes, there can be some operational criticism. Why? Because SR means shared randomness could be a resource in a classical information process. And actually, in our group, we had two results. One, the first one is saying that increasing the amount of SR could be powerful when there is no communication at all. If two parties, Alice and Bob, they do not have any amount of communication resource, just by increasing the shared randomness, they can do some classical information processing tasks in a better way. This is one. And the second one is saying, not only increasing the SR without communication, even adding SR could be powerful when assisted by communication. So these two results is actually hints that SR could be a resource in the classical information processing. So this could be an operational criticism to assume that unbounded amount of SR. And these are the main platform or main stage where we are trying to start our talk. So for this, what I will try to say in the next time, in the following, that is some, so you see that there are already some results in our group, and there is some another result by this Heinossari and other guys. So what the talk, or what is the next of the following of the talk will do, it will give a actual mathematical framework that how to characterize the difference between a classical and quantum communication, not just by giving an example, but giving an actual framework, a constructive framework. That is the main goal of our talk. So for this, that one of the most important thing is that the channel matrix, what we have written earlier. So this means that you have some input P1, P2, blah, 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 PM, and you have some output M1, M2, blah, 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 Mn. And what you have some probabilities that whenever the input is 1, the probability of getting the output is 1. And the input is 1, the probability of getting the output is n. And like that, you have a finally m cross n matrix. M row corresponds to m possible preparations. N columns corresponds to n outcome observable, or n property in an observable with n distinct property in general. And what the basic thing you can say about these matrices, all the elements of these matrices are non-negative. And if you sum any of the rows, what we will get that the input is fixed to 1 and you are trying to sum over all possible outcome 1 to n. That should be 1, right? These kind of matrices are generally called row stochastic matrices. In the following of our talk, whatever we will talk about, we are only considering these row stochastic matrices, or sometimes I will refer them as channel matrix. And one important thing about the next session of discussion, that you see, all the elements of these channel matrices, are non-negative. This kind of matrix we generally called as non-negative matrix. So I am saying this is important because do not confuse this non-negative matrix or like with positive semi-definite matrix, what we generally understand by this eigenvalues kind of thing and others. So whenever we'll talk about non-negative matrix, sometimes in the next session of the talk, we mean that a matrix where each of the elements are greater or equal to 0. And by saying it is a row stochastic matrix, means the sum of the all elements in the row will be sum up to 1. This is the thing. Well, now start with a simple thing that is called ultra-weak measurization of row stochastic matrix. These are completely, at least for at least 15-20 minutes, whatever we will discuss, that are completely about matrix manipulation and nothing else. But in the intermediate time, I will try to give a hint why it is connected with that kind of physical picture. So suppose you have two matrices, B and A. You will say that B is ultra-weakly measurized by A if you have two row stochastic matrix L and R such that B equal to L, A, R. So A is a M cross N matrix, B is a X cross Y matrix. Then L should be a X cross M row stochastic matrix and R will be a N cross Y row stochastic matrix. Now there is a powerful thing. I will say it first and then try to argue that why it is true. Suppose you consider any arbitrary theory. So you can first understand that if this A, it is a row stochastic matrix, it is actually a communication matrix or a channel matrix. Now, if any theory with dimension D can simulate a row stochastic matrix A, then it can obviously simulate B if B is ultra-weakly measurized by A. If the channel matrix B is ultra-weakly measurized by A, and you have a physical system by which you can simulate the row stochastic matrix or the channel matrix A, you can obviously simulate B with the same system of same dimension. Now we'll try to argue that why it is possible. So this is kind of a calculation, what we have tried to show, that suppose ultra-weak measurization of row stochastic matrix. So it means we are writing it in a density matrix and measurement formulation, but you can always think, since the classical is a special case of quantum, so this representation is at least general for classical and quantum theory. So actually, if A, hello, is there any question?
Hello.
Is there any question?
Yeah, yeah.
Uh,
So, as you said that this is a ultra weak measurization.
mhm.
So, is this just a convention, or I mean, is there any example of normal measurization here? I mean, why it is called ultra weak measurization? Because what you are saying that B can be produced from A
Right, right.
if there exists some L and R.
Right.
So this is you term it as ultra weak
Oh,
measurization.
okay. Now I understand it. Why it is called ultra weak. Yes, that part actually I have not discussed in this total in the scope of this talk, because it will give you a pre-order, means the ordering of a set, right? So if you
Yes.
take this measurization as a as a relation between two matrices, it will not define an order on this set of matrices. It will only define a pre-order. Maybe that is one reason why they have said it at ultra weak measurization.
Okay. Okay.
Mhm.
Hello.
Tamal, one point.
Yes. Hello.
Okay, first Arindam can go and then Nirmanda. Arindam, you had to ask some question. Okay, not responding. Then Nirmanda, you can ask.
Hello, am I audible clearly?
Yes.
Okay, but Tamalda, actually the normal measurization will also give you pre-order, right?
Because the symmetric thing is not happening, right?
Huh?
The symmetric thing is not happening, right?
Yeah, symmetric thing
Yes.
doesn't happen for
Yes.
measurization as well.
Okay. Yeah.
It is also a pre-order, not a partial order.
Right. Yes. Yeah. Then I don't know that why it is saying ultra weak, but obviously, yeah, I will try to see that what is the.
Yeah, because it seems like a normal measurization.
Mhm. Okay. Yeah. And I think Nirmanda was talking about something.
Yes, I was saying the same thing as Arindam said.
Okay. Yes. Yeah, okay. I'll try to find that why it is called ultra weak measurization. I don't know.
One of the reasons can be like when you talk about the measurization, then what happens is that you talk about with permutation matrices, you take a convex combination. Now what happens is like I think that can happen is like if it is strongly measurizable, that means the usual measurization, then you can always have this ultra weak measurization, but not the other way around. So it is actually generalizing this idea of measurization, where you have taken that L and R to be row stochastic matrices. I think that some kind of a generalization is happening over here.
Okay.
Because if it is measurized, then there will be a relation with entropy also.
Yes.
Because if A is measurizing B, then the Shannon entropy of B will be greater than the Shannon entropy of A.
Right.
Yes. But I don't know what kind of a relation will hold over here if it is ultra weak.
Yeah, I talk about the monotones under this measurization.
Yes. There will be some monotones over here.
Yes. Okay.
I think Snehasis has a question. You can ask.
Hello, Tamal, can you hear me?
Yeah.
So I was just trying to make sense of this equation that B can be written as row stochastics matrix multiplied by A multiplied by some another row stochastics matrix. So basically it is saying that if A is the channel, the sender can, before sending through the channel, the sender can
Exactly.
encode.
Exactly.
Yeah.
I understand. Right. And actually, I will also try to explain that. Yes. So you are saying that
basically a
he
data
can
processing
probabilistically mix some of the preparations and probabilistically keep some of the measurement outcome, right?
Yeah, and also the decoder can apply a
yes,
channel L.
exactly.
So if
Exactly.
the communication channel is independent with the sender part channel and decoder part channel, it cannot increase capacity. So it's actually a data processing inequality, right?
Yes, yes, exactly, exactly,
Hmm.
exactly. Great. Yeah,
Right.
I'll also talk about that. Right. Well, so I am not going to this total. I first initially put this calculation, then I realized that, well, that have no meaning, at least in this kind of a talk. What you can finally see that if you assume this kind of a thing, then if this AKL, the initial one, can be written in form of a trace of rho k ml. Rho k is a preparation and ml is a effect. And if you apply this rho stochastic, L and R in both sides, you will get a Bij, which is also in the same form as Snehashis was mentioned. It is some different preparation and different outcome. What is this different preparation and different outcome? That I will come to later. So just give you first two examples. Consider one matrix A3, which is basically 0. This is kind of a matrix A3. And this is another matrix G42, which is also in this form. Now, you do not go to this matrix multiplication. You just believe me that you can see that if you multiply L and R from the left and right to G42, you will exactly get A3. Now, what is the interpretation of this? I'll try to give the interpretation or how to see that this will actually work. You see, if you want to get A3 from G42, you can do. You can have many possible way to get A3 from G42, but I am suggesting one way. Suppose if you can forget about first three lines in G42, first three rows of G42, then so you forget about first three rows of G42 and then add these two columns in G42. You add the first and second column and then just alter between the fourth and the sixth column. So like this, forget about the first three column, sum over these two column, forget about the first three rows, sum over these two column and get an alteration between the fourth and the sixth. What you will get, that is exactly A3, you see. You can just check because this, by forgetting about these three, it will have this 3 cross 3 matrix. If you sum over these two columns, it will be 1 1 0 1 0 1 0 1 1. And now if you shift, means if you permute between the fourth and the sixth row, you will exactly have A3. And you see what L is actually doing. L is putting a 0 block here. So since you multiply L from G of the left side, this 0 block will actually vanish this upper term. And what it actually means, you see, this is kind of this is a swapping between this particular row and this particular row, because this one is now, if you consider this particular block matrix, you see this is exactly off diagonal. So the second row remains intact and the first and the third row, means here the fourth and the sixth row, get permuted. And what R is doing, you see what R is doing, R has taken this first two column to be add, right? And second and the third column remains unchanged. So this is just the mathematical logic and how this mathematics of the matrix multiplication giving this thing. But what does it actually means? You see these matrices importantly, and now we'll give a physical meaning of this thing. Suppose you have 6 preparations and a measurement device which has 4 outcomes. So as Snehashis has nicely pointed out initially, it's very good that if you want to get A3 from G42, you are actually doing some manipulation. What is the manipulation? You consider the left-hand side, this L matrix here. What is that? You forget about the previous 1 to 3 preparation. You forget about this preparation because there is a 0 block. And now you shift between 4 and 6 and remain 5 unchanged. Mean in the new version, there is no first three block, there is only 1, 2, 3. Now 1 becomes 6 and 4 becomes 3 and 2 remains to be 5. Instead of 1, 2, 3, you can think is as exactly 4, 5, 6. Means now it will be 6, 5, 4. So there is no problem. And what you are doing here, initially you have 4 outcomes, 1, 2, 3, 4. Now you see the matrix R, what it is making, it makes both of the first 2 rows in the associated with the first column. So 1 and 2, both the outcomes comes to a single outcome 1. 3 becomes 2 and 4 becomes 3. Instead of that, if you want, you can say that this is my 3, this is my 4. There is no problem at all, because you see this part is actually diagonal. So this point to this point keeps intact, and this point to this point keeps intact. Only the thing is that you add 1 and 2. So what actually happening, whenever Alice and Bob try to generate G42, Alice is sending one of the possible 6 preparations. Bob wants to measure a 4 outcome measurement. Now from that, if they want to simulate A3, what will happen? Alice will never send 2 or 3 preparation. Instead of that, whenever it is the 5th preparation, it is the second random variable, Alice will send the 5th preparation. If it is the first random variable, Alice will send the 6th preparation. And if it is the third random variable, Alice will send the 4th preparation. And similarly, in the decoding side, what Bob will do, he initially has a 4 outcome measurement. Now, he will only perform 1 a single outcome, 3 as 2, and 4 as 3. This is the whole thing of the row stochastic matrix ultra-weak measurization. Well, so as I have already said, and also by Nirmanda, that there are some monotones under this ultra-weak measurization. You can find these monotones. Actually, this is a screenshot from this paper by Heinossari and Kerpo, which is recently, maybe 2-3 days back, get accepted in Quantum. So that's why there is a peculiar reference here. You do not bother with these references. You can go to their paper and you can actually find these references. So what could be the monotone under this measurization? It could be rank. There are some max monotone, mean monotone, blah, 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 some few things. What actually we are interested about the monotones of this ultra-weak measurization are these 2 things. One is the non-negative rank of a matrix. Non-negative rank of a matrix. Whenever we will say matrix from now, we always mean that non-negative matrix with all elements greater or equal to 0. Do not confuse it with the positive semi-definite matrix. And the second thing is the positive semi-definite rank. We generally represent one of them as rank plus A and rank PSTA. So these 2 particular monotone is really important for our discussion. Why? I will see now. So first define the the non-negative rank of a non-negative matrix. That what is linear rank? This is the smallest number of vectors such that every row or column of the matrix can be written as the linear combinations of them. And what is non-negative rank? You have a simple demand that what you are talking about initially, the linear combination, that should be non-negative linear combination now. So that should be only the non-negative combinations. So you collect smallest number of vectors such that every row or the column of the matrix can be written as the non-negative linear combinations of them. For instance, if you consider this matrix, you see this matrix is actually a rank 3 matrix. Why? Because if you consider this one is a column, this one is a column, and this 3 column. And if you put a negative sign before the first column and add the second and third column, you see all the 4th column you can generate easily because you put a negative sign before the first column. So 1 minus 1, this is 0, and this is 1 minus 1, this is again 0, this will be 1, this will be 1. So by putting a minus sign before the first column and adding the second and third column, you can exactly get the fourth column. So the rank of the matrix is 3. But to get the fourth column, you have to put a minus sign before the first column. Can you make it with only positive elements? You can do a simple calculation and you can see that there you have to take all the 4 columns to generate them. Means there cannot be a subset of 3 columns. By taking the linear combinations of whom you can generate matrix. So the positive rank, so the non-negative rank of this matrix is actually 4. So this one is actually important for our discussion, this non-negative rank of a matrix. Now consider the non-negative rank of a row stochastic matrix. Suppose I have a row stochastic matrix, it's a colorful picture. What does this mean? That Alice has, suppose, red, green, and blue, 3 information. And Bob has to decode 3 out information, red, green, or blue. And the thing is that whenever it is red, Bob will say red with 3/4 times, blue with 1/4 times, and blah, blah, blah. Now there are 3 rows, and now I am asking that what is the non-negative rank of the row stochastic matrix? So first consider the first row, that is 3/4, 0, 1/4. What does this actually physically means? It means, see, it means the preparation is red. Bob will see the color that the object has red color, and with 3/4 probability or 75% probability, Bob will say the color is red. With 25% probability, Bob will say the color is blue. There is no problem with that. Alice just send this red ball to Bob. They can simulate this row. They can also simulate the next row. How? Alice can send a green ball, and Bob will say green with a probability of this 1/8 something percent, and will say blue with the another percentage with this 7/8 probability. Well, I can give a physical meaning to this row. Now you think you see one interesting thing. If you add these 2 rows with a factor of half for this row and half for this row, you'll exactly get the third row. And what does this physically mean? That if Alice is given a blue ball, sorry, if Alice is given a blue ball, Alice need not to send a new ball. Alice can exactly send red ball and green ball with a probability of half and half. And Bob will do the same thing what he has done by seeing red ball initially and the green ball initially. So what does this mean? This means that this 3×3 matrix, to simulate this 3×3 matrix, Alice has to send only 2 color ball, red and green. Though there can be a blue ball, Alice will never send this blue ball. Alice will, whenever it is a blue ball, Alice will toss a coin. Half of the times she will send a red ball, half of the times she will send a green ball. So I'm saying that this is the intuition you can think that the non-negative rank of a row stochastic matrix is actually the classical dimension required to realizing this matrix. So this rank plus C, this is the non-negative rank, it is absolutely, it is a mathematical quantity beforehand. Now you are giving a physical meaning of this particular quantity. If you want to go to the throughout proof, you can consider this paper by 2017 by Lee and his collaborators or our collaborators in mathematical programming. And I haven't gone through this paper because it's somehow difficult for me to going through this whole paper, but I can, this is the intuition that how can you think that adding 2 rows, if you can add these 2 rows with some probability weightage and generate the third row, this means the system you require to generate this row and the system you require to generate this row is sufficient to generate this row. Meaning this particular channel matrix or row stochastic matrix is can exactly simulable by a 2-dimensional classical system. Okay. So Any question or any comments?
Yeah. Tamal, can I make a comment or should I?
Yeah, sure.
Yeah. I'm saying, let's say, little bit extend this idea.
Mhm.
So I have considered shared coin, half 0 plus half 1 1, classical coin.
Right.
Now look into the reduced probability, reduced part. Okay. Now reduced part is a matrix, is a vector, no probability vector.
Yes.
But instead of this probability vector, let's represent it as a diagonal matrix.
Sorry. Hello.
Hello, can you hear me?
Instead of the probability matrix.
Probability vector, let's represent it as a diagonal matrix.
Okay.
Okay.
But I
Now,
cannot have any meaning with this off diagonal entries right now, right?
So far.
Oh, okay.
So far. Okay. Now let's say consider a little bit higher dimensional coin, 3, and again some diagonal matrix and suitably represent an in this matrix form.
Okay.
Now, means what I'm trying to say. Now this positive rank, non-negative rank. So it might happen the higher dimensional coin state, its mutual information is less.
Right.
But this non-negative rank is getting increased. That's why you cannot transfer from here to here. Like this mid rank, you cannot increase.
Okay. So you are saying that instead of seeing the picture of communication, if I translate the whole thing in the shared correlation, can we
shared correlation? Exactly.
Such a quantity, which is actually saying that why this kind of transformation, even in our paper, also is not possible. Yes.
Because you see, non-negative rank is exactly mimicking this mid-rank kind of things. In certain sense, it's bipartite.
Exactly. Right.
It might little bit tricky things might we have to do, but it seems it's possible.
Yes, exactly. Because this is kind of a special version of this temporal point.
Exactly. This is very beautiful kind of condition, this one is.
Yes, and now I don't know whether I have time. I cannot finish it because there is even something interesting thing you will find, but that is more trivial. Yes. Anyone? I think there is a question.
Yes. Yeah. So, okay. I just wanted to understand this non-negative rank a bit. So, your non-negative rank is like when you have these positive mixtures of the rows can simulate the other row.
Yeah.
The another row, right?
Right.
Now, the coefficients are positive, but idea is that we can normalize them, right?
I actually saying about this, I actually missed something, that if you consider the non-negative rank of a row stochastic matrix, then actually this coefficient will come out to be probability.
Yes. So what I am saying is that you can only normalize it when the coefficient, when the the supremum is unique. Supremum of all the coefficients are unique. In that sense, that then only you can divide it with the largest coefficient, and then the sum of coefficients will be 1. Then it will be normalized, right? But it may happen that there may exist row stochastic matrix for when you represent the non-negative rank in terms of those coefficients, those positive coefficients.
Hello.
Yeah, can you hear me?
I miss your last point.
So what I say that there may exist row stochastic matrix where these positive coefficients that you are using to recreate the other row those the supremum of that positive coefficients is not unique in the sense that you cannot like normalize those set of positive coefficients.
See, I think can I add one point here?
Yes,
Please.
So the thing is that I don't know whether this is a correct way to state that each of the rows in a row stochastic matrix is basically a probability vector.
Yes.
So
exactly.
since they are positive probability vectors, you can talk about them as discrete distributions. So obviously they will be non-negative numbers and they will sum up to 1.
Right.
So the question is that even if it is like for example, when you're talking about that unique supremum is not present, the worst case that can happen is like for example half 0 half. Okay. So but then again you will get a normalization for that. If it is not possible, that means if it is not possible in that way, that you are not getting any non-negative coefficients to write it in that way, then obviously the non-negative rank will increase.
Yes, and then that is exactly equal to the rank of the number of rows of the matrix.
Yes, exactly. So that is what I'm trying to say.
Yeah, that's why I was also confused, but I somehow couldn't.
But the discrete probability distribution, which you are recreating by taking those linear combinations, positive linear combinations of other discrete probability distributions.
Yes.
Like you are saying that positive linear combination, you can always make it convex, like normalized.
No. I'm not saying that they are. See, the question is, if you take all probability distributions, that is a convex set. Now that third row might not be. We might not be able to write it as a convex combination of the first and second row, but that will mean that the non-negative rank is 3.
Yes.
That means you cannot express it in terms of the other two distributions. That means it is an extreme point.
But that is only like for non-negative rank, you only need positivity. Like why do you need convexity? You don't need convexity. Right?
No. Convexity will be automatically emerge for this row stochastic matrix. What I am trying to say.
Yes. Otherwise, it will not be a probability vector if it is not a convex combination.
In general, for a non-negative matrix, this is not true that it should be a convex combination. No. But what I'm saying that for row stochastic matrix particularly.
Okay. Thanks.
The thing is that what is happening over here, each of the rows over here is a discrete probability distribution. Okay. Now the question is that suppose we have a 3x3 matrix, and suppose I can write the third row as a convex combination of the first two rows. Then the non-negative rank of that matrix will be equal to 2. Now, the thing is that why it should be a convex combination? It should be a convex combination because otherwise that particular row, that is that third row, will never be a probability distribution and it will not be a row stochastic matrix. Since we are now considering only row stochastic matrices, then it has to be a convex combination. In general non-negative matrices, this does not hold true.
Exactly.
Okay. Yeah.
Okay, in fact, if you see, for example, in a 3x3 matrix, if you take the identity matrix, now all the 3 rows are extremal distributions. Extremal distribution means that all are deterministic distributions.
Exactly.
So that's why what will happen, any row cannot be expressed as the convex combination of the other two rows, because all of them are extremal.
Yeah, and that is also a row stochastic matrix.
Yes, that is also a row stochastic matrix, and in fact, it will be an extremal row stochastic matrix.
Yes, exactly. Right.
So the fact that the third row is a probability distribution and the elements of the third row sums up to be 1 automatically implies that whatever linear combination you do it for the first and second rows, it will be that also will be a convex mixture. That is
yes.
At least for the row stochastic matrices.
Otherwise, it will not be a probability distribution if it is not a convex mixture.
Okay, thanks.
I think Arun has a question. We can take one last question maybe today.
Yes. Commander, can you hear me? So, yeah, I want to understand what is the physical motivation regarding that you can write the third row as a convex combination of the first and second row. Is it so that you can generate all the statistics regarding the blue ball by just taking the convex mixture of the red and green strategies?
Yes,
Like
exactly. Means what I want to mean, again, I add to your point that if Alice is given the blue ball, Alice doesn't need any new symbol to communicate to Bob. For the blue ball, she can just send red or green.
Yeah. So
need any
yeah. So what is our ultimate goal? Our ultimate goal is to send a minimum communication dimension, minimum physical dimension, as well as we have to increase the payoff of the game.
No. There is no question of payoff because the goal is to simulate this matrix. It is not exactly, I haven't defined a game. So I don't know what do you mean by payoff. The only goal is you have to simulate this matrix exactly. That is the thing. And with how much less communication, you can simulate this matrix. We are showing, though there are three distinct things, red, green, blue, Alice requires only two things, red and green, by which they can simulate the total matrix.
By payoff, I want to mean like for the red wall case, Alice can infer correctly 75% time, but for the green wall, there is maximum of the time he makes wrong conclusion. So 1 by 8 times he makes correct guess, and there is mostly wrong guess. So this is not a good.
I think Arun, you do not confuse that every time information means that what I have also said very initially, that the information doesn't mean that given red, you have to understand red. It may be a task that given green, you have to understand blue or green. You doesn't have to realize red. You doesn't have to realize green very good. It may be a demand of a game that I am not saying that it is very physical, but I am saying that, well, hypothetically, this is the question because we are trying to give an instance where this classical and communication can differ, right?
Yeah.
So I am not saying that this is actually a physical game, that red should be understood as red, green should be understood as green. No. I'm saying that you have to simulate this matrix. With how much less resource you can simulate this matrix.
Oh yeah, thank you so much. I understand.
Yeah, so I think I cannot continue, but there is some a long remaining portion of this talk, and
so
if you want to say something immediate and just show 1 or 2 slides, and then it should be okay. No, Shuradeep?
Yes. Or otherwise, Tamal, if you have time, you can continue next week also. Then we can.
Yeah, I think it is better to continue in the next week because I couldn't even finish the at least to the goal of the result. I think I need another week, obviously.
Okay, so then next week also, 14th, we will continue from here. Manikda and Snehashish has 2 questions. So maybe 2 last questions before we sign up.
Yeah, Tamal, very quick comment. Even the off-diagonal term, how I was saying, has a meaning. Because I was giving you the extreme correlation, half 0, 0, half 1, 1. You think it is P1 0, 0 plus P2 0, 1, 1 plus Q2 0, 1 plus 1, 0, then the off-diagonal will come.
But the off-diagonal thing, you are talking about the local part, right?
A local part, it will vanish.
Yes, because local part is finally classical, right?
Exactly, I understand. But this, you see, this, we should not say it is a trace out kind of things, but it somehow it is capturing that part that we have to bring.
Okay. Okay.
That's why I'm thinking how to do
You are
that.
saying that what could be the possible way?
Could be the possible way, so that it capture that thing, so that this mechanism or this for theory what they are trying to develop, that could have good application even in shared randomness level.
Yes. That is one important thing. Right. Mhm.
Okay.
Yeah. Who else has? Ashish.
Yeah, Tamal, can you hear me?
Yeah.
So I was thinking that in normal, when we calculate Shannon, then we have this data processing inequality that if in the decoder part we apply one more channel, then the mutual information will decrease, will be a monotone. You also talked about this monotone here. So intuitively, we know that an independent channel on decoder and encoder should be free. So now if you are discussing Frenkel Weiner, this is single shot scenario and the scenarios are bit different, not exactly like Shannon. So there is not a single merit like mutual information, but entire channel matrix is there. So I was just thinking, even intuitively in this scenario also the encoder and decoder part, independent channel should be free. But is it still not important to prove mathematically that if I apply independent channel on decoder part or on encoder part, the channel matrix will not expand. The space of all channel matrix, space of all probability generated on the decoder part will not expand. Don't we still need to prove that?
Rather the opposite thing. It may expand because you see, you can get this matrix just by a perfect communication matrix, right? When Alice is sending red, Bob will say always red. Alice is sending green, Bob will see green. So this is basically an identity matrix. But you can expand this matrix. So this expansion is always okay.
Okay, I was telling expansion in terms of if it expands, then some information will be increased if I apply an independent channel on the decoder side.
Some
Totally,
information will be increased. How you can say this?
because I mean, when we calculate set of all channel matrices, we calculate in terms of encoding probability and with respect to decoding random, just like we calculate Ix given Y, right? So if the channel space of channel matrix expands, that means given a encoding random variable, I can know more functionals about decoding random variable, right?
I couldn't follow your argument. Maybe
So
you are.
I mean, it's very intuitive to take further channels on decoding side to be free, but isn't like just like data processing inequality, shouldn't it be proved that it is indeed free? Are there any papers there that have proved data processing inequality for single shot channels?
I think by the definition of data processing inequality,
It follows some definitions.
because the definition is only considered about this mutual information thing, right?
In terms of in asymptotic limit in Shannon sense, it only concerns about mutual information. But in single shot, mutual information is not enough. So in single shot, people still need to prove in terms of all the functionals that are possible from a channel matrix. So,
but this weak majorization condition, what is ultra weak majorization condition, what Tamal is mentioning, isn't it in some sense capturing what you are trying to say?
It's capturing because I think either they can prove that if ultra weak majorization happens, then the channel matrix doesn't expand, or they have just intuitively taken it as free. I'm just saying
No, they have proven it. They have proven it. Yes.
Yes, everything has proved. That's why I am saying that you can go to this paper and follow the reference 30, 22, 22, 27, blah, blah, blah. So this is the screenshot. But I am trying to give you an intuition only. Yes.
Yeah, understood. Okay, thanks.
Okay, so we have to go for the
Okay.
next day, right?
Okay, yeah, maybe
Yes.
today hold all of your thoughts until the next week, and let's end today's discussion here. And Tamal, it will be nice if you give again in the next week.
Yeah, no problem, no problem.
Okay. Okay. Thank you.
Yes, yes,
Bye.
Tamal, it was a very good presentation. Very
thank
interesting
you.
presentation.
Thank you. Thank you.
Okay. Bye again.
Bye.
Bye. Bye.
Right.